Hello, welcome to Kyle Codes episode 2. This episode is on Two Sum, the binary search method. So in the last episode we were working on Two Sum problem on LeetCode.com. So we're going to look at that again, we're going to revisit it, and we're going to kind of improve the algorithm based on one of the hints they give us. So I'm going to reread the problem. Alright, so this is two sum. Given an array of integers, return indices of the two numbers such that they add up to a specific target. You may assume that each input would have exactly one solution, and you may not use the same element twice. Example, given numbers 2, 7, 11, 15, target of 9. Because nums 0 plus nums 1 equals 9, we're going to return the indices 0 and 1. Okay. So previously we did it kind of following hint 1, which is a brute force method. So we're just scanning and then scanning again for the comparison number. So we're scanning for index 1 and then we're scanning for an index 2, which when you take the elements at those indices, they sum up to our target number. So let's look at hint 2. Alright. So if we fix one of the numbers, say x, let's say x is basically nums I, or nums, let's say nums I. We have to scan the entire array to find the next number, y, which is value minus x, because x plus y should be our target value. So where value is the input parameter, can we change our array somehow so that this search becomes faster? So we're searching an array for value minus x, which could just be some arbitrary value. We're going to call it y, or nums j, so our second indexed value. So can we change our array so that this search becomes faster? Well, what comes to my mind is the binary search. And I'll show an example of a binary search right down here. Okay, something to note is this array is sorted, or ordered in ascending fashion. So let's go through a normal scan, which is kind of what we did in the previous episode. So using the scanning method, let's search for 15. So the first element is not 15. So let's exclude that from the array and just take the rest of it and search that. So our algorithm is basically compare first value of array to our target value of 15. If it's not equal to 15, exclude that and look at every other value in the array. So let's do that again. 4, not equal to 15. So let's exclude that and look at the remainder. So our first value is 6, not equal. Look at the remainder. 7, 9, 12, 15, 20, 26. And then we'll continue to do that until we find or get to the point where the first element in the array is 15, which is our target value. So that took 1, 2, 3, 4, 5, 6, 7 iterations. Okay, that's fine. That works. It's not super efficient, so let's speed it up a bit. Let's do a binary search. So the way a binary search works is instead of excluding the first value of the array each time, we're going to exclude half of the array, nearly half of the array. So the first iteration of binary search, we're going to take our array, the entire array, and we're going to cut it in half. And we're going to compare the middle number to our target value of 15. So 9 is not 15. Well, because I said earlier this array is sorted, we know that if 15 is in the array, it's going to be after 9. So let's exclude all of this because we know it's not there. So now this is our new array, and I copied that down here. So let's repeat that step. Divide it in half, so we actually have a blank spot because there's an even number of elements. And we use, because it's integer division, because the size of the array is an integer or number, we're going to divide it by 2, and then we're going to round down. cut it in half and round down, I guess would be a better way to say it. Okay, so let's look at the middle middle element. Oh, that's 15. Okay, we found it. So that only took 2 iterations compared to our 7. That's much faster. Now, there is a catch to this. The array has to be sorted because we need to know that when you divide it in half, all elements after it are greater than the number your midpoint. So that is the catch. It has to be sorted. If it's not sorted, it may be worth sorting the array for certain algorithms, and it may not. So let's begin with that. Okay, so now we're going back here. Okay, so we're reached this point. We know nums is not null, so we can continue. So the first thing we want to do is sort our array. Sort our array in preparation for binary search. So to keep it kind of short and simple for this episode, I'm just going to use array.sort. And that's kind of the built-in CSharp array sort. I might have an episode later on where I go through a couple sorts and compare their run times in certain situations. But for now, let's just use this because that's not really what this one's about. So let's sort that. Sorts the array. Well, you can't see that pop up. I should try to fix that. Okay, now our array is sorted. So we can binary search it. Okay, so we're going to loop through each number of our array. Let's write down an input array just for reference. Example nums array. The one they gave us was 2, 7, 11, 15. Oh, 2, 7, 11, 15. Okay. So, kind of walk through the algorithm. We're going to look at 2. I'll write this out. Look at 2. The num to find, based on the hint they gave us, is target minus nums I, which is the current number we're looking at, which for this case equals target of 9. So 9 minus 2 equals 7. So the num to find is 7. Search array for 7. Okay. Go through each number. I is the current index in our iteration. Nums I is the current element in our iteration, which is just using our I index to get the actual number in the array. This is just rearranging the equation again to find what our num to find is, which is going to be nums j in the previous example from last episode. So okay, so num to find is target minus nums I. Nums I is our current element in the array. Good way to find the good way to find num to find that we talked about is binary search. So let's use binary search in this example. There's other searches we could use. There's other ways to do this. We'll in the next episode we're going to look at another hint on this problem and do an even possibly faster way. Okay. Let's do this. Binary search. And we are going to search nums. Let's be consistent in naming functions. And we're going to search for num to find. And we're going to return the index from that. So, let's see. Let's create a new variable. Int index 2 equals -1. index2 equals the result of our binary search, which should return the index of num defined if it exists. If it doesn't exist, then we just keep going. And we'll make some efficiencies. I know we already have result defined, so we'll make some efficiencies before I end the episode. Okay, so now we know to break out by checking index2. Index2 does not equal -1, which is our really escape value. Then we can break. Okay, so let's define our binary search function. So let's create a static function that returns our int binary search, pass in an int array, array to search. Let's be clear in the naming. Int num to find, or target, or whatever you want to call it. Okay. Mark it up a bit. Write some comments. Okay. Use binary search algorithm to find num to find an array to search. Return index if found. Otherwise, let's do return index if found. Otherwise, -1. So now people using this function can really tell how it's supposed to work. It's always good to add comments in case I come back to this code in 5 years and forget how to use it. Array to search, I don't need to add comments because the name is array to search and you know what that is. Num defined, same thing. Returns, let me just copy paste this here, just be clear, it's probably not necessary. Okay, let's start the algorithm. So, define our index equals -1. Return our index. So this should work. Well, this code will not work completely. So let's go back to our code. If index2 does not equal 1, break. We're now out of the for loop. So we need to know what equals. We need to know what our result is. And that is an array of 2 integers, and we're going to return our 2 indices. Right. Index 1 and index 2. So index 2 is available, index 1 is not, because that's our I value. So I'm actually going to move this in here. Put that right here. Okay, so if index 2 does not equal 1, our index 1 is actually I, and our index 2 is index 2. Good. Excellent. Let's do our binary search, and I believe this code should execute and run correctly once we have that done. Alright. Oh, I actually wanted to make a note on array.sort before we continue. If you press F12 on this CSharp function, it's a library function basically, press F12, or if you have a weird keyboard, you can right click and say go to implementation. No, that's not right. Okay, go to definition, and it'll show you in the DLL possibly some comments on it. So what this function does is sorts the elements in an entire system.array using the system iComparable 1, I don't know what that is, don't worry about it, generic interface implementation of each element of a system array. So the generic interface implementation we would be using is an integer implementation, integer comparable implementation. I believe the default is just ascending for integers. I could look that up later, give more info on that if necessary. So the parameters, first one is our array, the one-dimensional zero-based system array to sort. So good, we're doing that correctly. The type parameter, this is this function has a type argument, or it's what is it called? I can't remember what it's called. Anyways, t is the type of elements in the array, which for us would be int. So we could also be more clear. And, oh, I'm sorry. And define the type of array we're using, but it can actually assume that based on the input itself, which is an int array. So we don't need to do that, but you could do that. It's just good to read through these comments just to know how the code could react and what exceptions it could pass. Sometimes there's useful info in here that you want to know. So some exceptions that we could have is the argument null exception, which is the array's null, but we luckily already checked if our array is null, so that's good. System invalid operation exception, one or more elements in array do not implement the iComparable generic interface. I don't think we're going to have that problem because int definitely defines that, and we could possibly find that. iComparable in 32. I believe it's going to be these. Yeah, it's going to be this function right here, which is the compare to, which should be in this iComparable interface. That's right. Compare to int t other. For us, that's going to be comparing to another int, so we can just look at this. Okay, so this is going to compare this instant to a specified 32-bit signed integer and return an indication of the relative values. A signed number indicating the relative values of this instance and value. Return value description less than, what is that? This is weird. Okay, this isn't completely clear, so I'm just going to skip that. But the important part to know is int does implement the iComparable interface. We just saw that. And the way we saw that was by going to definition of int and looking right here. It does implement iComparable. Good. Done. Okay, now that we have talked about sorting, I want to talk about sorting more. So another place to find info is to go to the docs.microsoft.com website, and you can look up array.sort or whatever function you want to look at, or interface or class or whatever you want to look at. That's part of the assemblies provided in Visual Studio. There's pretty good documentation on here in the .NET framework. So, okay, we're going to be using the sort array, and there's no other arguments we're passing. So let's just look at that and kind of look at the documentation. So, sorting the array sorts the elements in an entire one-dimensional array using the iComparable implementation of each element in the array. We already know that because we looked at the comments. Parameters, we already know about that. Oh, there's a new exception we didn't see before, which is the rank exception. If the array is multi-dimensional, you'll get a rank exception. We're not going to have that problem because it's a single-dimensional. One-dimensional array, we could have a two-dimensional array like that, but we don't have that. So we're not going to have this problem. Okay. Examples. The following code examples show how to sort the values in an array using the default compare and custom compare that reverses the sort order. So if we needed to sort our array in descending, this is the place. You could look here for an example of how to do that, but you just implement your own compare function, which is right here. Reverse comparer. There it is. Reverse comparer, which implements the iComparer interface. Some other info that I wanted to talk about real quick is in the remarks section. It says each element of array must implement the iComparable interface. We already know that. If the sort is not successfully completed, the results are undefined. This method uses the introspective sort algorithm as follows. If the partition size is less than or equal to 16 elements, which we will likely have for our example, but we could create a monster array to search an example of one of these other sorts. It's going to use the insertion sort algorithm. And I might do an episode later talking about each of these because that might be cool. But that's a pretty Pretty intuitive sorting algorithm. Here's a good image. I don't know if you could see this. It looks at each element and sorts it based on the previously sorted elements. Super intuitive. Runtime's not great, but it's pretty good for small arrays. It doesn't really matter at that point. If the number for this particular sorting algorithm that we're using from the DLL, what is it? System.array, the system DLL. If the number of partitions exceeds 2 times log n, where n is the range of the input array, it uses a heap sort algorithm. Otherwise, it uses a quick sort algorithm, and I believe these are both average time of n log n, where insertion sort, I think, is n squared. What's the runtime? Okay, worst case performance, average performance, O of n squared. So yes, so heap sort and quick sort are going to be a bit faster, especially for large arrays. Okay, this implementation performs an unstable sort. That is, if 2 elements are equal, their order might not be preserved. In contrast, a stable sort preserves the order of elements that are equal. For arrays that are sorted by using the heap sort and quick sort algorithms, in the worst case, this method is an O of n log n operation, where n is the length of the array. Right, so that's kind of what we were talking about. That's a faster algorithm for large arrays, as opposed to the insertion sort, which would be O of n squared. And if you don't know what big O notation means, that's kind of like worst case rounded performance. So n is the size of the input, and O of n, O of this, so basically O and then parentheses and then close parentheses means worst case scenario is n log n rounded. So you've kind of eliminated constant values, because as an array becomes extremely large, like millions of elements in it, the constants don't matter anymore. It's just the size of the array. Things that are dependent on the size of the array become ballooned so much that the constants don't matter anymore. And I could make an episode talking about big O notation at some point later. But for now, I think that's enough info on the sorting algorithm we're going to use that's provided by the system DLL for C#. That's great. Good stuff. Okay, now that we are sorted, we can use the binary search algorithm. Now I've pulled up the Wikipedia binary search page for the algorithm they provide, which is pretty good. I like it. If I need it for reference, we're going to go back to that. So if this isn't working properly, we're going to go back to that. But I'm just going to try to wing it for now. All right. So the way we're going to do this is we're going to continuously divide array in half on a, I don't want to call it a pivot point. Let's say a midpoint. If the midpoint is our target value, we're done. That was fast. Good. If the midpoint is greater than our target value, then we want to use the left half of our array. Okay, we want to use the portion of the array. Well, let me put this on a new line. Then use left portion of array, because that is going to be if the midpoint is greater than our target value, that means that we've already passed, because it's a sorted array, we've already passed our target. So we're going to look in the left portion of the array. Otherwise, the only other option is the midpoint is less than our target, and in that case, we want to use the right portion of the array. And we kind of saw that down here doing our example binary search. So that basically covers it. Now, one thing we have to look at is this is going to loop forever, and that's not good. We want to stop looping at some point. And how we're going to do that is we're going to keep track of our midpoint, and at some point, well, let's worry about that later. Continuous divided array. Okay, while true, so let's keep looping for now until I can wrap my brain around how I want to do that. Continuous divided array half. Okay. So let's get our midway point. Midway, or what do we call it? Midpoint. Initialize it to -1. Okay, midpoint equals. I guess we need to probably have a. What do we need? We need like a range of values, right? Yeah, let's have a start. Just kind of while I'm working this out. Let's have a start point. Well, let's say 0 because it's a 0-base array. Endpoint equals rate of search dot length -1. Okay, so we're looking at the very start of the array and the end of the array. Now let's calculate our midpoint. Okay, so that's going to be endpoint minus start point divided by 2. We need to surround this by parentheses. And that should floor it because it's integer division. So that's good. That's done for us. Otherwise, we could do a math.floor of the whole thing. It's not necessary, but I'll just put it in here. Oh, it doesn't even. It's an integer division, so it doesn't even let us use it. So we don't need that. Good. Okay, so let's fill out this part. If array to search midpoint equals our target num defined. That's what we called it. Then we're done. Turn our index. Else the midpoint is greater. Midpoint. Okay. If midpoint is greater than our target value, num defined. Use the left portion of the array. Else, we know that it's less than our target. Midpoint is less than our target, so we can use the right portion of the array. Cool. So the way we're going to do this is when we say use the left portion of the array, we're kind of, I want to draw a picture of this. So let's have an example array. 1, 2, 3, 4, 5, 6, 7, 8. So let's say our pivot is 4, right? How do we use the left portion of the array? So currently we have something like this. So our very start point, which is our start point variable, points to this, and our endpoint points to this. We want to just use 1 through 3. So we kind of want to do something like, I'll just do it here. We want to do something like this, and we want to just include 1, 2, and 3. So the way we can do that is by setting our endpoint, which is this marker right here, to midpoint. That's 4 is our midpoint. We could set our endpoint to midpoint -1. Let's do that. Endpoint equals midpoint -1. Okay, And we're going to kind of do the same thing here. 2, 3, 4. This is just an example array, so we can, because I like to visualize things as I'm working on it. Okay, so right now we've got something like this. Everything is encapsulated. We want to use the right portion of the array, and let's do this. 4 is the midpoint. So we want to have something like, oops, midpoint. Because we know the target is greater than the midpoint. So the midpoint is less than our target. We want to just basically move to only include this part of the array, which would be 5, 6, 7, 8. So it looks like the way we do that is we set start point to m plus 1. So let's do that. Equals m plus 1. Okay, that looks pretty decent. That looks about right. Things might work. Maybe we could run through an example of this. But we still need to know when to stop. So how do we know when to stop? So the way we know when to stop is we're going to keep doing this, and at some point, well, let's just run. Let's do an example of this. Let's run through an example of a. Well, I'll keep the algorithm here, right here. I'm going to put it right here. Here's our array, 2, 3, 4, 5, right? And we're looking for 6. Target of 6. So that's not in the array. So how do we know when to stop to know that it's not in the array? So we're going to start with something like this. Midpoint. Like that. Target is greater than our midpoint. So we are going to, what are we going to do? Midpoint is less than our target. Use the right portion of the array. Okay, cool. So we're going to do this. Now this. Midpoint is going to be 5. I'm sorry, 4. Okay. So now what happens? Our midpoint is 4, target is 6. The midpoint is less than our target again. Let's use the right portion of the array. So we're going to have something like this, where 5 is the only thing inside of the array. Okay, 5 is the only thing in the array. So our midpoint equals, the index is 0, 1, 2, 3, 4. Start point equals 4. End point equals 4. Okay, so one thing we could do is, if we get to the point where we're looking at our midpoint, the start point is 4, the end point is 4, and the midpoint is 4. That might, that indicates that we've reached the end of our search if our midpoint and start point and end point are not our target. So let's go to, okay, if we're ready to search midpoint, okay, so if we're reaching a point where we are looking at a situation like this, where the midpoint is less than our target, and we've also reached the endpoint. So if our midpoint is greater than or equal to, I'm sorry, let me think about this for a bit. Okay. All right, so the way I think we should do this, let's try it. And it might not work. I might have to go look at the Wikipedia search algorithm, just because I'm kind of doing this off the top of my head, or what makes sense in the moment. Let's think about it this way. If our num to find is greater than our midpoint value, then we're in a situation opposite to this. So let's draw that out as well. No, let's not. I'm just having a brain fart. Bear with me. Or don't. That's fine as well. Okay, let's just do this. Let's try this. So, say we're in this situation right here. When we hit this point, we will hit this point because midpoint is less than our target. So our target is greater than our midpoint. So our target is 6, midpoint is 5. So we're going to hit a point, a very strange point, where there's like an inversion, a flipping. So the start point, we're going to set equal to our midpoint plus 1. But that's kind of crazy because now it's past our end point, right? Our start point will be 5. Let's draw this out. So we're going to have something like this. We're going to have something like that. So that's probably when we know we can stop, right? So once we increment, well, let me write this out too. Midpoint equals, we don't have a midpoint yet, it doesn't matter. Start point equals 5, endpoint has not been changed from the previous loop, equals 4. So that's looking kind of crazy, that's not right. So let's say if start point is greater than point, we can return -1, right? Because it's not found. We've passed our endpoint. We've inverted. Reality has been flipped, and there's no hope for salvation at this point. So we're going to do the same thing here, but we're going to kind of flip it. I'll do another example. Let's do this. Well, let's leave an example number off. And we're going to say target of 1. Midpoint again is this one. We're going to hit here. Midpoint, mid value is greater than our target of 1, or num to find. So we're going to look at the left half. Like that. Midpoint is going to be 2 because it rounds down. We're going to keep going. We're going to look at the left half. Actually, when we get here, endpoint, midpoint -1. So let's do that. So it's going to be like this now. The midpoint is 2. Well, midpoint is 2 because it's the only value in the array. So that's still greater than our num-defined 1. So endpoint equals midpoint -1. So now we're going to have something like this. Endpoint is less than endpoint is less than start point, so that's not good. So our inversion of start point and end point. So we could say if start point is less than end point, turn -1, right? No. End point is less than start point. Because this is our endpoint. If that's less than start point, return -1. We have not found it. It's not there. Unreachable code detected. So that we get that warning because all code paths will result in returning value. So we can actually remove this fallback return. So yeah, I don't know if this is going to work. Okay, apparently this isn't being used. We don't need that. Now, okay, I want to make a note. I didn't follow the Wikipedia binary search algorithm. This is probably more efficient. I'll say for sure this is more efficient. Follow this exactly. This is boiled down to the best way you can do it. The way I did it, well, first of all, I don't even know if it's going to work. Second of all, we have a couple variables that are possibly not needed, right? Because they here just have L, which I believe is start point, and R, which is end point. So midpoint, storing that, possibly, oh no, they do store it. Okay, so we do need that apparently. Good. Well, anyway, there's probably some efficiencies, like such as these, the comparison. the order of comparison. So they say is the midpoint value less than your target, then cut the array in half and use the right half of the array. And then the next step is to check for mid value greater than target, which in that case we would use the left half of the array. So we do the same thing, but the order of comparison is different. This is probably slightly more efficient mathematically, algorithmically, whatever you want to call it. But this probably works, and there might be a couple iterations that are unnecessary in my approach, in this solution. But that doesn't matter for now. Maybe we could tweak it a bit at some point. Maybe I'll make another video at some point in the future. But that's well, let's try it. Let's just try it. I'm gonna stop talking. Let's see what happens. Found match 1 and 0. Okay, so that worked. Looks good. Let's try. Let's create a new array. That's pretty crazy. And let's do it unsorted. Just add random numbers. And I'm gonna just okay, and I'm gonna have the let's pick a target value of 56 plus, well, there's another 56. Let's do why do I keep doing duplicates? 234s. Let's do 57 plus 11. 66. No, I'm sorry. What was it? 57 plus 11 is 68. Let's try this and see if it gives us the right values of 0, 1, 2. Oh, 0, 1, 2. So there's our 11. 57. Oh, crap. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 19 and 2. Let's see if that works. Or if everything explodes, there might be an exception. Oh, this looks like an infinite loop. Wait, is it not? Is it just running? No, it's looping. It's looping. Alright, let's see where it's stuck. Okay. Array, midpoint index is 6. The value there is 6. Num defined is 67. Wait. Let's I'm debugging it right now, so I don't know if this is useful for anyone. I paused it because it seems to be infinite looping, so I've paused it during execution. I'm gonna check out the call stack so we can trace back to exactly where it's stuck. So obviously it's my two sum function that I've made a mistake. There's a bug in it. So num defined is 67 because our num's I of and i's 20 current, wait, i's 0 got stuck on the first value of 1. Okay, so it's looking for 67. Now in here, we can watch it loop infinitely. So let's start the loop over and watch it break. Okay, midpoint 6 equals endpoint 19 minus 7, so that's going to be 12 divided by 2 is 6. Okay, good. So our midpoint is 6. The value is 6. Num defined is 67. So it does not equal that. What was it? 6? So 6 is less than 67, so it should stop here and go through that code. So let's watch it. Good, good. Cool. Start point equals midpoint plus 1 Okay. Start point is greater than end point. It's not. Turn -1. Else, keep going. Point. Okay, start point 7. All right. So there's a logic error. It's looping because I made a mistake somewhere in the algorithm. So if people are watching and you've already figured it out, good on ya. I'm gonna look at it because I'm an idiot and it takes me a long time to figure this out. So let's bear with me. Okay, so endpoint minus start point divided by 2 is actually getting the this is getting the distance between them, and we're dividing by having the distance between them. And what we probably want to do, now I could be wrong again, I'm just kind of trying stuff. We probably want to try adding that to the start point. Otherwise, we're just setting the midpoint to the halving of the distance between the start point and end point. But that's not right, because if you look here, watch our algorithm. Right here, the midpoint should be set to here. But if you look at the distance between them, that's 5 minus 1 is 4, so set the midpoint to 4 divided by 2 equals 2, so index is 0, 1, 2, so here's the midpoint. Now the next midpoint is going to be, we want to set it, we want to set the start index. Okay, the start index is now midpoint plus 1, so that's right here. So that's 0, 1, 2, 3, 4. So our start index is 3. Now the midpoint should be here. So if we do start point minus end point, that's going to be 4 minus 3. That's 1 divided by 2. That's going to round down to 0. So that's going to be right. That's actually going to be here. But we want to add that to the start point. We want to put midpoint start point plus the half distance between them. So we want to put it here as opposed to here, which is where I was putting it. So that's a logic error. So we're going to add it to the start point. Okay, let's see if that works. There might be more bugs. Okay, it outputs something. Okay, we got 18 and 20. I didn't expect that. Or I'm sorry, 18 and 10. That doesn't even sound right. That sounds wrong. Let's see what numbers those are. 18 and 20. So if we're still debugging, so possibly we could look at this. 18, 56 plus 10 is 12. Oh, that's right. Oh, I was hoping for 57 and 11, but there's actually 56 and 12, so that works. So that's good. So I'm gonna change this because I don't want to get those values. I want to get the other values. 17 and 7. That's not right. Why did that happen? 17 and 17? Well, that's correct, but it can't be the same value. So let's find out how that happened and debug that, and then hopefully that's the last bug and we can end it. And then on the next, well, I'm getting my head of myself. Let's debug this. Okay, so how do we prevent it from having the same index for both indices? Because that's not right. Okay, so let's kind of walk through the code and figure out how that happened. Oh, you know what? Actually, I believe in the problem. They say there's no duplicates. You mean, oh, no, they don't say that. Okay, they don't say that. So we need to have a way of excluding the index that we're on currently. So if we're binary searching, we don't want to return we don't want to return the same index. Oh well, this is a tricky case. If the answer is a multiple of 2 and you have you have that value divided by 2 in the array, it's going to find itself twice. So we need to exclude that index. So there's possibly a better way to do it, but the way that's just coming to my head while I'm working on this video is just passing in an index to exclude. And again, there's probably a better way to do it, but I just can't think of it at the moment. So let's do that. Oh, index of exclude. Let's say excluded index. Okay. Number define target. So I. We want to exclude our I, because that's the current value we're adding to. So let's try that. So in our binary search, we want to exclude this index. So if it equals it, return it. Now, how do we? Okay, what's the right way to exclude this? Let's see. You know what? Actually, let me rethink. Let's do a shift. Let's change it up. Okay. Now, this is a special case we're talking about where I was an idiot and I put in a target which had its value divided by 2 in the array. So that's a special case, because if you get to the point of binary searching, you know it's in there. You know it's in there because you've already found it once. So let's just do a special case handler which is going to cut out all this somewhat long running processing and do something even simpler. So in our special case, before doing any of this stuff, let's say if target is divisible by 2, and this is the what is this called? What is this called? God. I can't remember what this is called. This gets the remainder of division, basically. So if we divide by 2 and the remainder is 0, which means it's an even number, and how do we do this? Let's do it like this. Okay. So if it's divisible by 2, let's first search the array for 2 occurrences of its this isn't gonna work. I'm still thinking. I'm still trying to find a better way to do this. So just give me a moment while my brain spins. Okay, screw it. Let's do this. Let's do the excluded index. But how do we do it? How do we implement it? Where's the best place to add that here? Let's think. Think for a moment with me, please. Okay. Let's think about this. Okay. Because it's sorted, we need a special case. So let's say index 2 is returned by binary search, but it's equal to I. That is an indication that we have the same index being used twice. So same index is being used twice, which is not allowed according to our problem statement. So this is a special case. Now let's visualize this again. So, well, let's use the array we have actually. So we actually have 34, and we're looking for 68. Oh, there's actually two 34s. This is perfect. Okay, so we're looking for 68. So we found our first 34, and we returned it as our index 2, but we were also on index I. Now, this array is going to be sorted, so it's going to be more like, let's do this. This could be wrong, slightly wrong ordering of the elements. That's okay. Just for the principle. And then whatever comes after. So this is a snippet of our sorted array. We're going to have 23, 34, 34, 35, 37. Okay, so in this case, I is here, and also index 2 I'm going to call J. They're both on the same thing. So when they're equal, because it's sorted, we know that if there is another 34, it's going to be either right after it or right before it. If it's not, it's not in the array. So, in this case, let's say if index 2 equals I, we're going to look at I'm not sure if we even need to look at the one before it, because if I and J were here, I would have hit this first and stopped. It would never hit this. And J could possibly be the second one, and then we wouldn't have this problem. So let's just focus on when they're both the first instance. So if nums I plus 1 equals nums I index 2 equals I plus 1. So this is the case where indexes are the same and we have two values after each other. If we don't, then this will not be true. Nums I plus 1 will not equal nums I. In that case, we did not find a duplicate of value, so it looked more like, I'll copy this. So it looked more like, let's just say, let's just have it like that. It looked like this, else, and this is I. Nums I plus 1 does not equal that, so we didn't find our value. So I'm going to set index 2 to our escape value again. Continue the search. So I think this should work. But there is a possibility of I plus 1 stepping out of the array. So let's also check if I plus 1 is less than or equal to nums.length, and no, it should be less than, not equal to. If it's equal to, then we've already stepped outside the array. So okay, so I think this should work. I think this should work. Let's try it and see if it works. 16 and 17. 1, 2, 3. I'll just look here. 16, 17. 34 and the next 34. Good. That's correct. Okay, so if I take out 134, well, I'll change it to a 36. That hopefully should give us the 57 and the 11. See if that works. 10 and 19. 10 and 19. 11 and 57. Okay, so that's the expected answer. So I'm going to call it done for now. So, okay, that's episode 2. Good stuff. Learned about binary searching. We solved the two-sum problem using hint 2. Good work. To me, I did it. Next time, I want to do hint 3 on the same problem and kind of explore the idea of using additional space, possibly a hash map, to speed up the searching of our second value. Instead of binary searching for it, maybe we could use a hash map, or in CSharp, a dictionary, which is, I believe it's the same as a hash map, but different. You can use things other than strings to index and have as values. So if you guys have any questions, leave it in the comments. If you have any suggestions, if this code is shit, feel free to trash talk it. Wait, can I even say that word? If the code is not good, if you do not like the code, if you have suggestions to make it more efficient, if I did something wrong, if you see a bug, please tell me, because I'm trying to become a better person in every aspect. And this helps me. This makes me a better person. So if you have feedback, again, if you don't like the code, if you have a question, comments, if you want to make fun of me, you can make fun of my nose. Feel free. Or if there's errors, feel free to comment. Again, next time we're going to do hint 3 of the two-sum problem from LeetCode.com. I don't have anything else to say, so I'm ending it. Goodbye.